This 3D printed antenna tracker will track the quad across the sky using the quad's GPS latitude and longitude and the quad's altitude. It tracks it by decoding the Frsky Sport Telemetry, which is available on the Taranis S-port pin and also the Frsky R9M S-port pin. Inside the lower casing is an Arduino Uno, which is running a library that I wrote in C++. The library decodes the Frsky S-port telemetry. The Uno also runs a sketch that transposes the telemetry, latitude and longitude of the quad, and also its altitude, into a bearing from the tracker to the quad and an angular vertical bearing to the quad. The sketch further transposes those into angular movements of the vertical and horizontal servo in order for the tracker to follow the quad across the sky. You can see that the tracker can hold various components. One is the RC832 together with an helical antenna. Another is a RunCam2 camera, and also a mobile phone can be slotted into the third type of holder. On the back of the tracker there is a 2S power socket, the Arduino Uno programming port, a switch which in the upper place is for programming and in the lower position for running, and a power socket at the top for powering any object device that you have attached to the tracker. The tracker communicates with the S-port of the Taranis or the R9M module by means of a Bluetooth module, an HC05, set to master at a speed of 57,600 baud, internal to the tracker, and a similar Bluetooth HC05 attached to the Taranis. And this is set up as a slave. The Bluetooth on the Taranis is enclosed in the yellow box that you see there. The black wire connects to the ground, the red to the 5 volt and the orange to the S-port of the R9M module. The S-port data is inverted, so we need to have an inverter between the R9M module and the Bluetooth. I used a 2N7000 to do this, and I copied this circuit diagram from one that I have found on the internet that used the same item. You can see that the 10K requires 3.3 volts for outputting to the HC05 Bluetooth module, and the 3.3 volts is able to be picked up from the HC05. Again, I've copied this diagram from the internet. It was the same as I have done, so I haven't reproduced my own, but you can see the 2N7000 is easily mounted on the HC05 module. The tracker does not need a compass of its own or a GPS. It will obtain its bearing from the quad, and to set it up we place the quad and line it up onto a distant object and power up the quad. We then place the tracker and line the tracker up to the same distant object. The tracker is powered up with a switch in the program position, which is up. The Taranis is set down and powered, and the Taranis will communicate via Bluetooth with the quad, with the tracker, sorry. When the quad has got a GPS fix, the switch on the tracker is moved down to the run position, and the tracker will obtain the bearing from the quad, which is the same as the tracker because they've been lined up on the same distant object, and will also obtain the quad's GPS position, which is the same as the tracker because they are reasonably close. The tracker will now track the quad, which I've got in my hand, and as I move across the garden, the tracker will move and track the quad. I have slowed this part of the video up slightly, probably at half speed, in order for you to see the reasonably smooth movements of the tracker. The general construction of the 3D printed parts is shown here. In the upper box there are two axial bearings in the right hand and the left hand holders. The servo is shown in the centre. In the lower box there is an upper thrust bearing, and below that is an axle bearing. Again, the servo is shown there. The individual components in each of the boxes, as I say, are available for 3D printing, and they are on Thingiverse. A link is provided below. The lower box has a casing into which is fitted two holders for the servo. The servo bolts onto the holders and the servo arm slots onto that. It is important to set the servos up to 90 degrees before you install them. The servo arm plate goes on top of the servo arm, and that screws onto there. A shaft goes onto the top of that, and there is an axle bearing holder. That's the bottom cover of the holder. This is the axle bearing holder. The bearing is a friction fit into it. Again, the bearings that I used are shown below, and into the top holder goes the thrust bearing. and the shaft goes down through them both onto the servo arm. Per box, the base is shown and a backplate is screwed onto the base. The hole there houses the power outlet. The two sides hold the axle bearings. The bearings slot into that holder there, and the shafts go in and through the bearings. It is important that a washer, shown in a moment, goes on the left-hand side of the shaft, and then the bearing, and then the washer on the right-hand side. These are on both shafts, the left and the right, and they ensure that the moving parts do not come in contact with the fixed parts. The bearing, as I say, slots into that holder there and is a friction fit. The bearing covers go on, they're not really needed, but they're there to stop the bearings slipping out, although I find they are quite tight. And there's a bearing cover on the outside as well. Onto the base is fitted the servo mount. And the servo is screwed onto the mount. The servo arm slots into the servo arm holder, and the servo slots into the servo arm. It is important that the servo is set to 90 degrees before you slot it into the servo arm. You cannot get the servo arm exactly in the correct place, angular place, because the spines on the servo shaft do not allow for it to be precisely set, but this is adjusted later in the software. You can see this servo in place there with the servo bracket fixed to the base of the upper box. It is all fitted very compactly, and as I say, the individual 3D printed items are on Thingiverse and are listed below. This is an exploded view of the insides of the upper and the lower box. It's quite useful to play this backwards and see how the components slot in to position there. An exploded view of the lower box, indicating how these components fit together. Once again, the tracker is compact, 3D printed, and will hold several items. The tracker is lined up on the distant object with the quad, and therefore can get its bearing and GPS position from the quad before it starts to track. And it will track the quad across the sky as shown in this garden demo. If we turn now to the software, install the Frsky R9M Sport Telemetry decoder library onto the Arduino, and there are three examples sketches. The first one is the decoder, which decodes all the telemetry that is available from the quad, as you can see here. You can then use this in your own sketches. The second sketch is the tracker, and if you set the debug to 1, this enables the print statements, and because the servos are not perfect, and because the servo arm doesn't fit exactly onto the shaft in the place that you would want it to be, there are some constants here that you need to use to map the servo arm correctly. For instance, I had to input 12 degrees for the servo to go to 0 degrees, and 153 degrees for the servo to go to 180. So you will fit your own constant values in there so that the servo, when it goes through its test, as it does from 0 to 90 to 180, actually goes to the correct place. You can see now that this is some of the information coming back when the tracker is in operation. The third example is a test for the tracker. This simulates various GPS latitude and longitude. The idea being that it simulates the quad flying north and gaining height, turning west and gaining height, turning east and losing height, coming back west and gaining height, and then coming back to home, which is south and losing height. And this is the information that you will get from that test. Turning now to the circuit diagram, you will see that the tracker is powered by a 2S battery, the positive of which goes to the in pin of an LM323T 5-volt regulator. The output from that goes to power the two servos. The battery goes directly to the Arduino Uno V-in, and 5 volts output from the Arduino Uno powers the HC05 Bluetooth master. The diagram says slave. This is incorrect. The TX from the HC05 goes to the switch on the rear. When the switch is open, it enables the Arduino to be programmed. When closed, the Arduino will run the program and decode the telemetry. Pins 11 and 12 of the Arduino go to the lower and upper servos respectively.